Using the idea of bond order, we can define some bond order, bond length like that. Okay. For example, if I have O2 plus, O2 2 plus, O2 minus, O2 2 minus. What about the bond order? The bond order of oxygen, that's 2. Because there is 16 electron. Here 15 electron, here 14 electron. So 14 electron 3, 15 electron 2.5, 15 electron 1.5, 14 electron 2. I'm sorry, 1. I'm sorry. This is the increment of electron, right? So this is 17 and this is 18. Okay. So if you are asked to arrange them in the bond, what about the bond order? Bond order increases like this. So bond length from here to here, bond order increase. Therefore, if you are asked to find arrange in bond length decreased. Or if it is in bond energy, then the bond energy increased. Okay, if you know the bond order, then you can find orders of other. Okay, this is very important. Question may ask like this. Ready? And mainly, but actually we actually want to find this bond order using what? By writing the configuration. So if you know the idea, just discuss in the last part, then we can easily predict this. Okay, fine. Ready. So now let's have a look at the molecular orbital diagram. Molecular orbital diagram. Okay. For example, for hydrogen. Hydrogen, the electronic configuration is sigma 1s2 less than sigma star 1s0. So if this is the energy barrier, and this is a pure atomic orbital of hydrogen atom, and this is another atomic orbital of hydrogen atom. Okay, so when they combined, there will be an orbital with the higher energy and another orbital with the low energy. Okay, fine. So listen, we know that this is a 1s atomic orbital, and this is sigma 1s, and this is sigma star 1s. So here 1s have 1 electron, this 1s also have 1 electron. When they combine to form the molecule, that 2 electrons in sigma 1s2, well, this is vacant. So this is how the molecular orbital diagram of what? Hydrogen. So now let's discuss the molecular orbital diagram of carbon. Due to carbon have 2s2p mixing, right? So what about the configuration of carbon? We know that 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, okay, less than pi 2p x2 equal pi 2p y2. Well, the other orbitals are sigma 2pz less than, well, that is vacant, pi 2px equal pi 2py vacant, and pi star 2px equal pi star 2py vacant, sigma star 2pz also vacant. Okay, so how we can draw this? Ready? Fine. Listen. So first draw this one. If this is the energy barrier, this is 1s, this is another 1s. When they get combined, form like this. Okay. Well, what about the 1s of carbon? What about the normal configuration of carbon? Carbon is 1s2, 2s2, 2p, x2, 2p white. So 1s is filled for each carbon. So each carbon, the 1s is filled. When they combined, they forms sigma 1s, sigma star 1s. Both are filled. So this will be like this. Next is 2s. What about the 2s of each carbon? 2s also filled. So for both carbon, 2s filled. And they combined to form the orbitals like this. Okay. Where this also sigma star, sigma 1s 2s2, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. That's perfect. Now P. What about the P? Here Px, Py like that, okay? Consider the p orbital. Let me extend this. If you consider the p orbital, there are actually 3 p orbitals. Are there 3 p orbitals where the electron arranged like this. Here also 3 p orbital. Okay. And they have a lower energy orbital and higher energy orbital. Okay. A lower, what about the order? Since due to 2s2p mixing, pi 2px, sigma 2pz. So among these 6 orbital, one with the least energy is sigma 2pz, where least energy is pi 2px equal to pi 2py, and sigma 2pz have greater, relatively more energy. So listen. This is the least energy is for pi 2p category, right? So this is pi 2px equal pi 2py, and this is sigma 2pz. Okay. Well, the most energetic one is sigma star 2pz, where to that comparatively less energy is for pi star 2px in anti-bonding. So here the topmost one is sigma star 2pz. Okay. Below that your pi star 2px equal pi star 2py there. Ready? So what about the electron filling? Sigma pi 2px2, this much is filled. This is vacant, this is vacant, this is vacant, this is vacant. So this is how your carbon. Okay. If there is no 2s2p mixing, what is the difference in diagram? If there is no 2s2p mixing, the difference in diagram, that is, here will be the difference. There will be the difference. That means lower energy will be sigma 2pz, and pi category have relatively more energy if there is no 2s2p mixing. Okay. So that's only difference. Ready? So this is all about molecular orbital diagram. So the next shapes of a molecular orbital. Okay. First one, the shape of s orbital. We know that 1s combined to form sigma 1s, sigma star 1s. Okay. So when they combine to form the sigma 1s, what happen means, when these two orbitals undergoes additive combination, the shape of orbital will be like this. Okay. Here is the positive nucleus. Ready? Positive lobe, which means the positive cloud of this s orbital, and this is the nucleus. where electrons are surrounded around nucleus. Okay, but if we consider the subtractive combination, what happen means the nucleus are get into the same direction, or nucleus become more closer. Ready? Nucleus become more closer, so that there creates a nodal plane. Okay, so there is a region where the probability of finding electron is 0, and moreover the nucleus get closed, so there will be a high repulsion which increases energy and decreases the stability of 1s orbital. So you simply study or simply identify the structure of what? Orbitals. Okay, so there is a nodal plane in antibody molecular orbit of sigma 1s. The very same structure is for 2s also. Okay, it is given in textbook like this. Ready? Actually the shape of sigma 1s is something like this. Here is the nucleus, here is the another nucleus. Okay, where electron density, a small portion of electron density here also, a large portion of electron density in between nucleus. So the nucleus have a greater distance, so that more attraction or electron density is more stable, or that orbital is more stable. But in case of sigma star 1s, the nucleus are like this, where here is a nodal plane, electron density situated away from the nucleus. So this, due to this nodal plane, means a region where the probability of finding electron is 0, the greater internuclear repulsion between them. Okay, so in your Ncert textbook it is given like this. Okay, the next, the very same kind of combination by what? PZ orbitals. Okay, your PZ, when the PZ orbitals undergoes additive combination, then this, here is your nucleus. Okay, then they brings a large orbital, where the nucleus are here. Ready? These two combine to form a large orbital, where the next is a small lobe like this. Ready? Fine. But in case of subtractive combination, here also electron density well situated in between the orbitals. There is no nodal plane for sigma 2pz. Okay, sigma 2pz. Ready? What about the shape of subtractive combination? If these two undergoes a subtractive combination, then the shape of the orbital is something like this. So here is a nodal plane, here is your nucleus. So here also a nodal plane, which increases the repulsion, where the electron density situated far away from the nucleus. Okay, that's why the stability decreases. Ready? What about the pi category? Pi 2px, pi star 2ps is given. The very same is for pi 2py and pi star 2py. Both are same. Okay. 1s, 2s, both are similar trend. Pi 2px, pi 2py, both are have same trend. Okay. So when a pi 2px and pi 2ps undergoes additive combination, then there will be a nodal plane. Above that nodal plane there is an electron cloud. Below that nodal plane there is also an electron cloud like this. Okay, so there is one nodal plane even if it is a bonding molecular orbital. But what about the anti-bonding molecular orbital? Anti-bonding molecular orbital, there is actually due to the subtractive combination, actually there is two nodal plane like this, which increases the repulsion more, which decreases the stability more. Okay, so there are actually two nodal planes. So two nodal plane is for pi star 2px and pi star 2py, and a nodal plane is for pi 2px or pi 2py. A nodal plane is for sigma star 2p az, and also a nodal plane is for sigma 2pz. So, sigma 1s or sigma 2s. Okay, so these all are the different shapes of molecular orbital. Okay, which is given. This is a figure which is given in your textbook. Ready? Okay, so next, the last topic is hydrogen bonding. So we want to discuss the van der Waals force, the special category of van der Waals force called hydrogen bonding here, and the dipole-dipole interaction, London force, and ion dipole-induced dipole interaction all are discussed in your stage of matter. Next is hydrogen bonding. Hydrogen bonding is a special type of dipole-dipole interaction. Dipole-dipole interaction. Special type of dipole-dipole interaction. So that's a strong dipole-dipole interaction between hydrogen and highly electronegative elements. Hydrogen and highly electronegative elements like fluorine, nitrogen, oxygen, rarely the chlorine. Okay, fine. Usually the hydrogen bond may take place between hydrogen and fluorine, or hydrogen bond represented by braked lines. It's a dipole-dipole interaction. Okay, well, this hydrogen bond have greater magnitude than between hydrogen and oxygen, or that one have a greater magnitude than hydrogen and nitrogen, or that one have greater magnitude than hydrogen and chlorine. Okay, for this interaction energy, the interaction energy varies from 2 to 10 kilocalorie per mole, which means 8.4 to 42 kilocalorie per mole. Ready? Fine. And this is introduced by Latimer and Rodbach. Latimer and Rodbach. Okay. There are two types of hydrogen bonding. First one, intermolecular. Intermolecular hydrogen bonding means, you know that, between two molecules. Intermolecular hydrogen bonding, the hydrogen bonding between two molecules. If the hydrogen bonding between two molecules, what happens? Association, molecular association increases. As the molecular association increases, boiling point increases, melting point increases, viscosity increases, surface tension increases, density increases, solubility increases, etc. Well, the next is intramolecular hydrogen bonding. Intramolecular hydrogen bonding means hydrogen bonding within a molecule. If the hydrogen bonding is within a molecule, hydrogen bonding which present in a molecule, that is said to be intramolecular hydrogen bonding. Okay, due to intramolecular hydrogen bonding, molecular association decreases, because hydrogen bonding which present in a molecule, and a molecule with the neighbor, there is no hydrogen bonding, so association decreases relatively. That's why boiling point, melting point, boiling point usually decreases, solubility, etc. the terms are decreases. Okay, fine. So let's find some applications of hydrogen bonding. Some different applications. Okay, the first application, HF exists as zigzag shape. HF have a zigzag shape. Okay, and that zigzag shape is like this. if HF covalent bond and hydrogen bond. So due to that hydrogen bond, it exists as zigzag shape. First point. KHF2 exists. So HF which exists as a polymeric form due to hydrogen bonding actually. Zigzag polymeric form due to hydrogen bonding. KHF2 exists, KHCl2 not. Okay, because in KHF2, I'm sorry, in KHF2 what happened means around hydrogen one fluorine connected by covalent bond and another connected by hydrogen bond, but that is not observed in chlorine. Okay, chlorine rarely shows hydrogen bonding. Ready? So here chlorine have no hydrogen bonding. The next, boiling point of H2O that is greater than ROH, that is greater than ROR. Similarly, and this is due to hydrogen bonding decreasing. The strength of hydrogen bonding decreases from left to right. Similarly, if you consider the boiling point of H2S, the boiling point of H2S is greater than RSH, which means boiling point of H2S is less than RSH. Where that is less than RSR. So here no hydrogen bonding. So as size increases, boiling point increases. Here even size increases, but due to hydrogen bonding strength decreases, a greater tendency here. Okay. So these all are why this is in a reverse order means here no hydrogen bonding in case of sulfur, but there is a hydrogen bonding in case of water. Okay. And moreover, water exists as a liquid because intermolecular H bonding is in water. So high molecular association, they exist in liquid. The very same similar hydrate H2S, this exists as gas because absence of hydrogen bonding. Absence of hydrogen bonding. Okay, that's an application. And the mixture of orthonitrophenol and paranitrophenol. Orthonitrophenol have low boiling point. Low boiling point because in orthonitrophenol the hydrogen, there is a intramolecular hydrogen bonding, but in paranitrophenol there is intermolecular hydrogen bonding. The hydrogen bonding is between another molecule, so high association, high boiling point. Okay, so here orthonitrophenol is steam volatile. So this method can be this mixture can be separated by steam distillation, since there exists two different types of hydrogen bonding, so that their boiling point is different. Okay, usually two OH are not exist in a carbon. Usually two OH are not exist as stable in a carbon, but in chloral hydrate is stable. Chloral hydrate is stable. Okay. Why the chloral hydrate is stable means there is a chance for hydrogen bonding, intramolecular hydrogen bonding between OH of H, OH and chlorine, where these OHs are trapped. So it won't eliminate as water. Okay. That's an application of hydrogen bonding. And we all know that the solubility, boiling point of primary, secondary amines, tertiary amines, that depends on hydrogen bonding. We already know that from your organic chemistry. And like that solubility of organic compound in water, that also depends, that all are depends on alcohol soluble in water, aldehyde soluble in water, ketone soluble in water, carboxylic acid soluble in water, amine soluble in water, because they all can form hydrogen bond with water. That's why they are soluble. Okay, they all are applications of hydrogen bonding actually, but it is discussed in corresponding organic chapters. Okay, fine. Next, I have an application. Say, benzoic acid as dimer. due to hydrogen bonding. So which increases the association, thus the boiling point. Okay, we all know that benzoic acid which exists as dimer. Why it exists as dimer means this is your benzoic acid which exists as dimer here due to hydrogen bonding, intermolecular hydrogen bonding. Okay, the next point, acidity of salicylic acid higher. Acidity of salicylic acid higher. Why salicylic acid is more acidic means, if this is your salicylic acid, more acidic means this electron easily donated to form the conjugate salicylate ion, where the salicylate ion is well stabilized by hydrogen bonding. Okay, so there are a lot of applications where hydrogen bonding involved. Ready? Fine. So that's all about hydrogen bonding. Okay. Now we can compare the properties of covalent and ionic bond. It's very easy. The properties of covalent and ionic bond. The properties of covalent and ionic bonds. Fine. Usually, covalent bonds are either solid, liquid or gas. Ionic bonds are usually ionic bonds, not ionic bond, ionic compound. Properties of covalent compound and ionic compound, the last topic. Okay. Usually covalent compounds are solid, liquid or gas. Ionic compounds are crystalline solid. Okay. For a pure covalent bond, covalent bonds are generally covalent compounds. In case of pure covalent compounds, compounds are generally polar, but ionic compounds are non-polar. Covalent compounds are non-polar. Ionic compounds are polar. Since covalent compounds are non-polar, less soluble in water. Less soluble in water because water is polar. Relatively, this is more soluble in water. More soluble in water. Okay. Next, no electrical conductivity because they won't ionize. Usually, generally, a pure covalent compound, which means not a polar molecule. Okay, here conductor at a molten or aqueous state. Okay, and this exists as isomorph. Okay, different crystals with a similar composition, but this exists as stereomers. This can exist as different stereoisomers in case of covalent bonding. These all are the main difference. Pretty. So that's all about your chapter. Now your chapter is over. Okay.